We've all seen functions in various parts of mathematics. At the basic level, functions are rules that assign elements of one set to elements of another set. And functions can tell us a lot about the relationships between various mathematical objects. Here we will review several ways to visualize functions and discuss some of their important properties.
Let A and B be sets. A function from A to B is a rule that assigns to every point in a point in B. This is written f colon A to B, where f of x in B is the value that is assigned to the point x in A. A is called the domain of f. B is called the codomain of f. The range of f, or the image of f, is the set of all points that can come out of this rule. More precisely, the image of f is all y's in B such that there is an x in A with f of x equal to y. Note that the image of f is a subset of B, but in general does not have to be all of B. Functions are also called maps and transformations, and this depends on the context and how we're thinking of them, specifically how we're choosing to represent or visualize the function. Let's give some examples. One way to visualize a function is using a graph. This is particularly useful when the domain and codomain of the function are both the real numbers, i.e. when it is a function from R to R. Here we plot the function f of x equals x squared. As we know, the graph of this function is a parabola pointing upward. Notice that above every point on the x-axis, there is one and only one point on the graph. This is the value of f of x. Another way to view a function is as an abstract map between sets. This is especially useful if the sets are finite. So for example, consider the two sets a and b, and we represent the action of the function with arrows. In each case, the point xi will map to f of xi. Note specifically, as represented in the picture, it is possible for 2 points to map to the same point under the application of the function f. Here's another example, one where we think of the function as a transformation of a set into itself. Consider the xy plane and the function that rotates every vector by angle theta. We can write down a formula for this function, given below, and we can see how this transforms the plane in this picture. We can also consider the action of a function on a subset of the domain and not just on an individual point. Let f be a function from A to B, and let C be any subset of A. Then we can define f of C to be the set given by f of x for all x in C. Since each point f of x lies in B, the set f of C is a subset of B. Moreover, in this notation, we can also write the image of f as just f of a itself. Here's another example of a function, this time on a finite set. Let a and b both be the set 0, 1, 2, 3, 4, and let us define f of x to be x cubed mod 5. Now we can compute these just by plugging in. F of 0 is 0, which is 0 mod 5. F of 1 is 1, which is 1 mod 5. F of 2 is 8 mod 5, which is 3 mod 5. F of 3 is 27 mod 5, which is 2 mod 5. And f of 4 is 64 mod 5, which is 4 mod 5. If we write these in a table, we see that the function just mixes up the numbers and each output appears exactly once. This is also called a permutation. Here's another example. Let a be the closed interval minus 3 to 3, and let b be the set of real numbers. Now consider the function f of x equals x cubed, which we have drawn here. Note that not every point in B gets hit, because the graph has a finite range. However, notice that we could shrink B, and as long as it contains the interval minus 27 to 27, this gives us a valid function. Some more definitions. We say that a function is injective or one-to-one if it never sends 2 points to the same place. More precisely, we say, for all xy in A, if x does not equal y, then f of x does not equal f of y. Writing this as a contrapositive, we can also say, for all x in A, if f of x equals f of y, then x equals y. We say that f is surjective, or onto, if every point in B is hit by the function. That is, for any y in B, there is an x in A with f of x equals y. Summarizing these two, note that surjective means at least one x maps to every y, and injective says that at most one x maps to any y. And finally, we can put these two together. A map is called bijective or invertible if it is both injective and surjective. This means that every point in B is hit by exactly 1 point from A. Also note, a bijection on a finite set is called a permutation. One thing that cannot be stressed enough, a function being injective or surjective depends not only on the rule f, but on the domain A and the codomain B. For example, if we consider the function f from R to R, where f of x equals x squared, we can see that this function is neither injective nor surjective. For example, it is not injective because f of 1 equals f of minus 1. More generally, f of x equals f of minus x for any x. It is also not surjective because we can never get a negative number to pop out of the function. If y is negative, then there is no x, such that f of x equals y. But let's modify the domain and the codomain without changing the function's rule at all. Let us now define a and b to be the non-negative real numbers. Now we can check that the function is both injective and surjective. For example, if x squared equals y squared, and we know that x and y are both non-negative, then we can deduce that x equals y. Therefore, the function is injective. Also, notice that every non-negative number has an x that maps to it, because f of the square root of x gives me x. Therefore, we've shown that f is both injective and surjective, and therefore bijective, when we choose this domain and codomain. So again, we did not change the rule, we only changed the domain and the codomain, but that made the function invertible. In fact, it turns out that this function does have an inverse. We'll talk about that more next time. One last example before we go. Let's choose A and B to both be the set 0, 1, 2, 3, up to 9. So all the integers from 0 to 9. Now, let us define f of x to be 7x mod 10. We can tabulate all the values this function takes, and we see that each value appears exactly once. The function is injective because nothing appears twice, and surjective because everything appears at least once. So this function is in fact invertible as well. Again, we'll talk more about the inverse next time. Also, let's finish on a modulo pro tip. The fact that this thing is invertible, the fact that this function is bijective, happens because 7 and 10 are relatively prime. More on this later.